Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on ARMA modeling illustrated with data examples. And in this lesson, I'll introduce another example, which is related to prediction of Alaskan moose population. And I will apply the ARMA models and forecasting for this particular data example. The population of wild moose in areas such as Alaska often fluctuates over several years due to both human-influenced and natural factors. While the fluctuations are rarely drastic across a given year, they do exhibit a general rise and fall trend over time. The end point of this study is to predict the Alaska moose population. In this lesson and the one following, we'll ignore other factors which may impact the rise or fall of the moose population. We'll simply predict using the total yearly moose population alone. In a different lecture, we'll consider other factors and compare the predictions from this lecture. Why is it important to predict the Alaska moose population? For many Alaskans, moose meat is the largest source of food income for a family, as a typical moose weighs approximately 1,200 to 1,500 pounds and provides a typical family with 500 to 600 pounds of edible food. Thus, it is of great importance to the Alaskan citizens to manage and control the moose population to ensure the sustainability of this population. Not only harvested by its food source, the moose is harvested for clothing purposes as well. Moose also serve as the important tourist attraction, which helps to bring several thousand people to this great state every summer. The findings established in such a study can be of particular use to the Alaska Division of Wildlife Conservation, which tracks populations of species across several years for scientific and conservation purposes. Currently, expensive surveys of the moose population are required every few years to approximate this population and set the appropriate hunting quota. The data provide relevant factors related to moose population, including population of Fairbanks, which is close to the location Unit 28, from which we have the data on moose population, Alaska wolf population, average snowfall, and moose harvested. Again, we will ignore these factors at this point, but we'll return to the study by accounting for these factors in a different lecture. The years of the data are from 1965 to 2006, and the data are observed yearly. The data come from multiple sources, but I'll particularly acknowledge the Alaska Department of Fish and Game. We begin by reading the data filed in R and converting the columns into time series. Because the data are observed yearly, the frequency for each time series is equal to 1. The time series plots of the factors in this data set are here. We'll focus on the total moose population in the study. We can see that many of the factors provided have some overlapping patterns with the time series of the total moose population. Overall, the total moose population had a fall around 1975, but it has increased steadily since then. There is a little volatility also. It seems that the trend predominates the behavior of this time series. Since trend is predominant in the variations in a time series across time, we'll explore first the first-order difference time series by plotting the difference time series along with ACF and PACF of this difference process. The plots are here. In the upper left plot, you'll find the regional time series to compare it to the difference time series in the upper right plot. While we see a clear trend in the original time series, one differencing is enough to remove this trend. However, we'll still see some patterns in the difference time series indicating that one order difference may not completely remove the trend or other patterns that could lead to non-stationarity of the time series. The ACF and PACF plots do not indicate non-stationarity. They both have only one lag outside of the confidence band, which indicates stationarity. We'll continue with the first approach by removing the trend and then applying ARMA to the detrended time series. To remove the trend, we'll use the splines regression approach introduced in the first lecture of this course. I first define the time points, which are simply equally spaced values between 0 and 1. Then I apply the R command gam for splines regression, where the gam is from the library MGCV. Note that in order to specify a non-parametric trend, we need to transform the time point vector using the S option in gam. There are other splines regression models implemented in the gam command. Make sure to read the help menu of this R command for other options. I then extracted the fitted values of the model to obtain the estimated trend and transform the vector of fitted values into a time series with the same time specifications as the original time series. Here we plot the time series along with the trend. We thus overlay the fitted trend on the observed time series values. I also plotted here the ACF and PACF plot of the residual process after subtracting the fitted trend. Here are the plots. In the first plot, we have the observed time series versus the fitted trend. We can see that the black line, which is the observed time series, is very similar to the blue line, which is the fitted line. The upper right plot presents the detrended time series. The detrended time series shows that the trend has been removed. The ACF and PACF plots show also that it is plausible that the detrended time series is stationary. Next, we apply the ARMA modeling to the detrended time series, called here the residual process. Similarly to other examples used in this lecture to illustrate ARMA, we'll first select the AR and MA orders using the AIC approach. We thus first feed the model for orders 0 to 5 for both the AR and MA orders, and then select the order for AR and MA polynomials such that we have a minimum AIC value. The selected orders here are 2 for the AR polynomial and 3 for the MA polynomial. Next, I fitted the final model with the selected orders. Here is the output for the test of uncorrelated data applied to the residuals of the final ARMA model. The p-values for this test are small, indicating that we reject the null hypothesis that the residuals from the ARMA fit are uncorrelated. Let's also look closer at the residual plots next. Here are the residual plots. We have seen before the R commands used to produce such plots and thus not provided here. The residuals versus time are patternless with lower volatility in the middle. Both the ACF and PACF plots indicate the possibility of white noise, and from the QQ norm plot, the quantiles of the residuals line up very closely with the quantiles of the normal distribution. Thus, while the test of the uncorrelated variables suggests potential correlation in the residual plots do not accept that the variability of the residuals may not be constant over time. In summary, in this lesson, I illustrated ARMA modeling with yet another data example, which shows the wide applicability of the ARMA modeling. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is illustrating ARMA models with data examples. And in this lesson, I will continue the data example of modeling the Alaska moose population with the focus on forecasting. While we have data on factors influencing the population of moose in Alaska, in this lecture we only focus again on the forecasting of the moose population without knowledge of other factors to compare later with predictions obtained using also other factors. I illustrate here how to obtain predictions using the approach when we decompose the process into a trend and a process model using ARMA. Here, we'll forecast the total moose population for 4 years, not on a rolling basis, but all 4 years ahead. We set aside the data for the 4 years and fit the trend on the remaining years. That is from years 1965 to 2002, and feed the trend based on this data. We predict the trend using the predict command. To apply the predict command, we need to first define the new data for which we seek to predict future values, those being the 4 years ahead. Note that when defining the new data, we need to define it as a data frame, and we need to specify that the new data is for the predictor used in the fitted model, here being defined as X. If you will not correctly define the new data as a data frame and do not specify correctly that the predictor is the one used in a fitted model, you'll have an error message. The residual process is now defined based on this fitted trend, since we assume we have not observed yet 2003 to 2006 moose population. The ARMA model is fitted on this residual process. We use the same orders as identified initially, although we should have applied the order selection approach once more using the data from 1965 to 2002. Next, we apply the predict command, but for the ARMA fitted model. Last, we sum up the prediction of the trend and the prediction of the ARMA model to get the final prediction based on this approach. We'll next apply ARMA modeling, which takes into account both the non-stationarity due to the trend and the ARMA jointly into one model. We'll specify only one order difference to account for the trend, and then select the orders of the AR and MA components of the ARMA using a similar approach as before. The final model is one where the ARMA polynomial order is equal to 1 and the MA polynomial order is 0, and a difference of order equal to 1. This is our output for the two tests for uncorrelated data. Similar to the previous fit on the detrended time series, the p-values of the two tests are small. However, they're not smaller than 0.05, indicating that we do not reject the null hypothesis at the significance level of 0.05. But because they're smaller than 0.1, we reject the null hypothesis at a higher significance level. We conclude that there may be some evidence to reject the null hypothesis of uncorrelated residuals. However, we need more data to conclude on the rejection of the null hypothesis. These are the residual plots from the ARMA fit. The residual plot is patternless, similar to the residual plot from the previous approach, with lower variability in the middle, indicating potentially non-constant variance over time. Both the ACF and PACF plot indicate the plausibility of white noise. The QQ norm plot, however, has a tail on the left, indicating that the normality assumption may not hold. Generally, we perform the residual analysis to assess goodness of fit. If there are serious departures from the model assumptions, the residuals will indicate that those departures, what those departures are, and thus on how to revise, adjust the model. Here, the departures are non-constant variance and possibly non-normality. Both could be fixed using a transformation of the white noise. We'll also learn about models for modeling non-constant variance in a different lecture. Here we continue with forecasting the total moose population using the ARMA modeling and compare it to the predictions based on the previous approach where we first fitted a trend and applied an ARMA model on the detrended time series. We first refit the ARMA model based on the data from 1965 to 2002, thus discarding the last 4 years. Then we use the predict command to predict the 4 years, 2003 to 2006, all at once. We'll next compare the predictions based on the first approach using trend estimation and ARMA to the second approach using a ARMA model. We first have to specify the minimum and maximum values of the y-axis through the y-min and y-max as on the slide to make sure that we plot the data and the predictions on the same scale. Then we plot the time series of the observed moose population for the last 2 years of the data, overlaying the predictions from the two approaches. Here's a comparative plot. The black line shows the observed time series for years 1987 to 2006. The red line is the prediction of the last 4 years using the first approach, and the blue line is for the second approach. While neither predictions capture the decreasing trend in the last 4 years, the first approach is much closer to the observed time series than the second approach. In fact, ARMA simply assumes an increasing trend, capturing the trend from 2000 to 2003. This is because the ARMA part of ARMA adds little to the prediction, since it is an ARMA model of order 1, while the prediction is primarily driven by the value of the last observation of the time series. So far, I illustrated the applicability of ARMA with 3 examples. The first example was for modeling and prediction of the volume of patients in an emergency department, an application in healthcare of great relevance for hospitals. A second application was the forecasting of the stock price of IBM, a common prediction exercise for many financial investment companies. A third example was in prediction of moose population, which can be used by environmental agencies to control the population of moose. Other applications from the fields of climatology, for example, forecasting temperature, from the field to economics, for example, projecting GDP, among many others, are subject of modeling and forecasting using ARMA modeling, but also other time series models, as we'll learn in the next lectures. Overall, with the 3 examples used to illustrate ARMA modeling and forecasting, I intended to show you some of the limitations of ARMA. ARMA modeling is easy to implement, but it captures the non-stationarity in trend, assuming similarity among prior observations, and thus it can mispredict if there are large changes in the trend. On the other hand, the trend plus ARMA estimation approach is more difficult to implement, particularly if interested in obtaining confidence bands also, but it can capture long memory trends. Prediction using ARMA can perform well if only short-time prediction periods are considered. This lesson concludes the ARMA modeling lecture with illustration of ARMA modeling with 1 example and an overview of the importance of ARMA modeling and its limitations. Thank you.